please go ahead.
Thank you, Raymond, for the introduction, and thank you for inviting me to give this talk. I'm really happy to visit Minnesota again with the University of Minnesota virtually. The first time for me was in person a few years ago, and I hope I will be able to visit in person soon again. Today, I will tell you about some recent work I've been doing in the last few years on the cosmological imprints about axions. By cosmological imprints, I mean the imprints on the CMB. That's why there is this nice blank background on my title slide. And I don't think I need to remind to most of you, but just to make sure we are all on the same page, the reason why I worry about axions, and in particular about the Qcd axiom, now axion may mean different things, but in this talk, I will be talking about the so-called Qcd axiom, and the motivation is the strong CP problem. The strong CP problem is our lack of understanding of why strong interactions are so good when it comes about time reversal invariance. And on the theory side, in the Lagrangian, this time reversal invariance is achieved only when we set these so-called theta parameters to an extremely small number, less than 1 part in 10 billions. So this is one of the most serious puzzles in fundamental physics, and the axiom comes as a product of one of the most famous solutions, if not the most famous, probably the most famous, the most elegant, which is the one suggested by Pechai and Quinn in the late 70s. So in this framework, there is a new global U1 symmetry, which is called U1 PQ, Pechai-Quinn symmetry. And this symmetry needs to satisfy two basic ingredients. First, it needs to be spontaneously broken at some scale FA. So I take this opportunity also to introduce these important parameters that will appear over and over in my slides. So this is a good chance to define that. So this is the scale where this new global U1 symmetry gets broken. And in particular, this is an energy scale which is much, much larger than the weak scale, and actually much larger than any energy we can achieve with experiments. And the second feature is that this symmetry must be anomalous under strong interactions. So the way the Pechai-Quinn mechanism works, in short, is the following. Here I have the energy scale, high energy on the top, low energy on the bottom. At the high energy, the axion is the pseudo-Nambu-Goldstone boson associated with the spontaneous breaking of the Pechai-Quinn symmetry, the field A. And since the symmetry is anomalous under strong interactions, I expect the presence of this coupling where G is the gluon. It's really the gauge boson of Qcd. Okay, this is the field strength of the gluon. This is physics high energy. Once we go at low energy, in particular, as low as the Qcd phase transition, the axion develops a scalar potential, which is a consequence of this anomalous coupling. And the full form of the potential is not really important here. I want to introduce another important parameter, which is the mass of the axion. And that's why I'm taking this harmonic approximation. And the axion mass is a number which will be very small, as I will show you in the next slide. So the way it works is the following. The axion field evolves in the early universe. We can track the evolution by solving the equation of motion. And Qcd dynamics itself drives the axion field to its minimum, which is CP conserving. And that's how the strong CP problem is solved dynamically. The axion mass, as I was saying, is very small. It's related to this scale FA, which is the Pechai-Quinn breaking scale. It scales like the inverse FA. And if you set for FA a number which is typical in these theories, for reasons that I will explain in well, first of all, because it's not excluded experimentally, and that's also the scale where we get the correct dark matter abundance, you see that the axion is very, very light. In this case, we have micro electron volt. So since I want to tell you about the imprints on the CMB, all I care about is that actually this mass is much less than the temperature of recombination. So for the purposes of CMB physics, we can treat the axion as a massless field, and this will be important for my analysis. So the axion is very light. it's also very weakly coupled because all axion interactions are suppressed by this large scale, since it's a pseudo Nambu-Goldstone boson. So the axion detection is very challenging, but there has been lots of novel ideas in the last 10 years, roughly speaking, that I do not have time to recover because it's an effort orthogonal to the one of my talk, but it's also something very interesting that's happening in the field. I would like to focus today on this other feature of the axions. Being very light and very weakly coupled, we can find some interesting physics in the early universe. And in particular, I will tell you about thermal hot axions produced in the early universe. And then we'll discuss how they get produced. I quantify how many we produced, and I will correlate with observables. Okay, so the topic of my talk is hot axions, but just one slide to remind you another good feature of the axion, which is the one associated to the population of cold axions. They provide a viable dark matter candidate. We know that dark matter must be cold. And in this famous plot, there is the requirement, the blue line or the red line are the requirement for the relic density. So in this horizontal axis here, we have the axion decay constant, Fa. On the other horizontal axis, we have the mass. Remember, they are related. So there is a one-to-one correspondence between the F and Ma. On this vertical axis, we have the axion initial field value in the early universe. This is a dimensionless quantity, and it's actually the axion field divided by Fa. Okay, so the point where you want to live in this plane depends on the interplay between the Patriarchal phase transition and inflation. If inflation happens before Patriarchal phase transition, so it's something that you can assume that it happened, the Patriarchal transition happens in a radiation-dominated universe, so there is no interference with inflation, then you need to live in this red band here. The reason why it's a band and not a point is because there is a large theoretical uncertainty, because computing axion density is difficult. On the other hand, if you are in a situation where inflation happens after the Patriarchal phase transition, then there is also dependence on the initial field value in our Hubble patch, because different Hubble patches will have different axion field value, because inflation will stretch them during this fast expansion time. And again, here, unless you have some reason to assume that this number can be very small, and there can be arguments why you can fine-tune the initial field value, but if you're not willing to take this option, then it's natural to expect also this initial field value to be of order 1 in these dimensionless units. And so you end up with values of F still in this range here, okay? So this is an interesting range because it's allowed by other bounds, such as the one coming from stellar cooling. It's a range where you can have dark matter as a viable, axion dark matter as a viable candidate. And it's the lower end of F. You see, F here is small compared to here, for example. So small f means larger couplings. And so the effect of the production of hot axions can be prominent. And so I will focus on this region of F. And I want to see if this population of hot axions can be a complementary probe to...
Don't you still get the bounds from stars in the blue curve? Why is it extending down to low FA?
Oh, sorry. This is I mean, low FA is on the right of the plot.
Yeah, that's what I'm saying. So isn't the bound it has to be bigger than about? Well, it's like the little red one. Why is it going past the endpoint of the red one? I'm presuming is coming, the lower bound is coming from stellar production, right?
No, sorry. The red band is only a requirement on relic density, but there is an uncertainty on the topological defects contribution. So that's okay, why it's a band.
But isn't that also about where the lower bound on FA
the is? Stellar bound is more like here. I will put stellar bounds in my plot. But it's
10 to the 9 or 10 to the 8, something.
8.
It's 10 to the 8.
Yeah,
Oh,
it's
is it
10 to
that
the
low?
8.
I thought it was higher from red giants, but okay.
Keith, it depends whom you couple it to, right? If this is a real FA that you couple to G mu dual, right?
Yeah.
When you, I guess there will be extra suppression when you couple it to electrons and something like that. So
Yeah. But I mean, I will when I will present
Yes.
my result for axions, there will be stellar bounds, so we can discuss
Okay.
there. But it's true that it depends on the analysis, and there are often differences which are a factor of a few between different analyses. So the stellar bounds they come with many caveats. Okay.
Okay.
So actually, I will show that the bounds I will put with the CMB are exactly in the same region, so it's good. I think it's good because they are more solid in this respect. Okay, and of course, feel free to interrupt me at any time. Okay, even if I don't say everything I want to say, I'm happy if we discuss. Of course, it's not the same as discussing in person, but we do what we can. Okay, so hot axions. So that's the main subject of today's talk. So why do they call them hot? They call them hot because they are produced from scattering and decays involving particles from the thermal bath. Here I have a scattering. Okay, these B1, B2, and B3 are imagined standard model particles. Okay, quark, leptons, gauge bosons. So these scatterings can happen when these particles are in the bath. So when the temperature is above the mass of these particles. So they are typically produced, this axion here, they are typically produced when the temperature is much larger than their mass. And so they are produced with a kinetic energy much larger than the rest energy. And in this sense, they are hot. These processes here can thermalize the axions or not. I will consider both cases. If they thermalize, they will not be coupled forever. At some point, they will decouple. And whether they thermalize or not, there will be a point starting from which they will just free stream, and they will propagate freely in the expanding universe along the geodesics, exactly as neutrinos do. And so exactly as neutrinos, the one with neutrinos is a good analogy because we can infer their presence in the CMB by studying the anisotropy spectrum and basically quantifying the radiation content of the universe at the time of recombination. This is historically parameterized as N effective. Okay, N effective is defined in this equation here. You see there is this ratio of neutrino temperature and photon temperature. So if you only have the standard model, this N effective is 3 plus some small corrections due to neutrino, the detail of neutrino decoupling. Okay, but N effective within the standard model is pretty much 3 plus small corrections. If you have additional radiation components, such as the axions, then you have to add a contribution, which I will refer to as delta N effective, which is basically given by the ratio between the photon energy, the axion energy density and the photon energy density, with these 3 factors that you compute very easily. So what I want to quantify, okay, because I care about things we can detect in the data, is what is the contribution of the axion to this delta N effective.
So
So
this
here
axion,
is
sorry. So this axion, if they're hot, they're going to erase density perturbations, right? So isn't there a limit on the mass, just like you do for neutrinos?
Exactly. Very good point. So I will show you that the region I'm interested in are such that you will never encounter this problem. But actually, I'm working now with cosmologists in Rome, and we are investigating region of the axion mass where this effect is important. So having the neutrino case in mind, you need an axion mass around 1 eV, more or less.
Exactly, yeah. Mm-hmm.
But I will show you my plots that the axion mass is actually always below.
Okay, so this
in this case is not an issue, but that's something we're doing now.
Oh, okay.
With people from the Planck collaboration. So yes.
Okay, so you'll have to give us another talk another time.
Yeah, hopefully in person. Hopefully in person. Okay. So here is an interesting plot that we produced in this paper from last summer, but there are many versions. Let's focus on the green line, because the green line is the scalar. Scalar means one internal degrees of freedom, such as the axion. So the axion is assumed to be in thermal equilibrium at some point in the early universe, and then it decouples at the decoupling temperature given by this TD here. And on the vertical axis, there is the contribution to delta N effective, which is a function of TD. And of course, the later they decouple, the larger the contribution is to delta N effective, just because the bath has less degrees of freedom. It's a G star effect, okay? It's something you can compute very easily. So just to give you an idea of what the experiments are doing now and what they can do in the future, Planck at the moment is sensitive to axions that decouple around the time of the QCD phase transition. And the target of future CMB stage 4 experiments is to investigate axions that decouple basically before the electroweak phase transition, okay? At some point, this line will get flat because at high temperature, of course, if you only assume the standard, this plot only assumes the standard model, they get flat. So as you can see from this plot, the details of decoupling can be important because G star is changing quickly below the weak scale. And even if you miss the decoupling temperature by a factor of a few, the prediction on delta N effective can be rather different. Moreover, axions may never thermalize. So this plot is not very useful if you are investigating a case where thermal equilibrium was never achieved in the early universe. So this is not what we used for our analysis. What we used was a Boltzmann equation to track the axion population in the early universe. And so the left-hand side is very famous. This is just the axion number density, the time derivative. This is the Hubble expansion. Our contribution from particle physics was to compute, which I call schematically as gamma, but these are just the rates from the different processes changing the number of axions. Once we...
I have a question. So there were lots of previous work done, right? I remember a few years ago, Strumy and collaborators have looked.
Oh yeah. I will show plots from Strumy and I will tell you what we improved.
Okay, very good.
Yeah. Okay, so delta N effective is proportional to the axion co-moving density, which we will reach an asymptotic value, and it will be proportional to this value to the 4/3 with a prefactor that depends on known quantities. Okay, so solving the Boltzmann equation will allow us to predict delta N effective. And of course, these rates here, they are model dependent because the axions, I told you, it couples to gluons, but it can also couple to other gauge bosons through very similar couplings with the field strength or to fermions as well. Okay, so every time I will show you plot, I will tell you what I did. Okay, so when it comes about production mechanism, I would just like to give you highlights, quickly highlights from these papers that are not the most recent ones. And these are also the easiest one to study. They are easy because if you couple to leptons or third generation quarks, you can basically ignore confinement. Okay, if you couple to leptons, you use perturbation theory. There is really, I mean, there are calculations to do, there are Boltzmann equations to be solved, but the prediction of delta N effective can be done with very standard techniques. Also, if you couple to third generation quarks, in the end, the bottom mass is large enough that basically by the time you reach to the confinement scale, axion production is not efficient anymore. And so you can basically neglect these complications. So these are the cases we studied first. Just two quick results from these two papers. The first one is the coupling to leptons can alleviate the Hubble tensions. In this paper, we did a fit with the Planck data, and we found that the tension between the two measurements of the Hubble parameters there was still some tension, but it was smaller than the one that is in the lambda CDM model. Okay.
Sorry, I have a quick question here.
Yeah.
So is this model different from the case where you just add some unknown delta effective? Does it have to be axion in solving the Hubble tension?
No, I mean, this is of course delta and effective. What we did the fit where we fit the scale FA as a fit parameters, and we provide a UV origin and a microscopic origin for delta and effective, but of course it's a delta and effective solution. Yes.
Okay.
That was known.
Okay.
Third generation quarks, top and bottom, as I say, they're very massive, so the effect is not that large. In particular, it's not something you can see with Planck. You can see in the future, and it's interesting because the region that you can see in the future, which is these values of FA, here I don't have the stellar bounds, but I will have in the next slides. But if you assume that all the dimensionless couplings of the axions are of order 1, so there is no hierarchy between different couplings, in particular, the coupling to photons is described by the order 1 coefficient with respect to the one of the third generation quarks. This is also a region that will be probed by the future axion haloscopes, which is this region here. Okay, so this coupling to third generation quarks is something that can be tested in the future, and it's a region that will be tested otherwise. But of course, here I'm assuming a single coupling at a time. And I was not very happy with this analysis because I wanted to study a full model, okay, a full axion UV completion and have predictions for these cases. Once we have a UV completion, although coupling to first and second generation quarks are model dependent, what is not model dependent is this coupling to gluons, okay? If you are really dealing with the Qcd axiom, and if you want to solve the strong CP problem, unfortunately, you have to deal with this coupling here. And this coupling carries many complications, as I will describe in a second. Moreover, for example, the DFS axiom, I will show you this case later. It couples to all quark generations, in particular to the first U. And for the first U, you cannot neglect confinement. Okay, because the mass of the quarks are not much larger than the GeV scale. Okay, the bottom case is already on the edge. Okay, but you cannot do the same as we did for this case for the first two generation quarks. Okay.
Sorry, could I ask a question here? I mean,
yes.
Why is the UV completion? The UV completion is only important if you reheat to above the PQ phase transition. Is that?
Oh, sorry. By UV, I didn't use maybe the best expression. I mean, of course, what the UV completion tells you is the relation among the different couplings. It tells you what couplings you have at low energy. Okay, yeah, that's what I meant by UV completion.
Oh, okay. So because you're still interested in temperatures below the PQ transition, right?
Always below, much below.
Yeah, much below.
If you thermalize above, you get delta and effective of 3%, 2.7%.
Mm-hmm. So yeah, it's just another way of just saying axion model dependence, right? So
yeah, so maybe I didn't use the best. What I meant is this C.
Yeah, the CX and the C psi. I see.
Exactly.
Yeah.
So what I did in the paper, I told you, I switched on one at a time, and the easiest ones. Okay. Now I want to take some framework like the KSVZ, like the DFS.
Exactly. Yeah.
And then I know that the C in that case are connected, and there is not just a single one.
Yeah, but you see, but in principle, the KSVZ, right, it has colored quarks. And so if you excite the extra colored quarks, then they would also
I will discuss that. I will discuss that. I will discuss
that.
I will discuss that.
I see,
yeah. But you know, these quarks are heavy.
Exactly. That's why I was wondering.
So the effect is not so, but yeah, I will discuss this actually very soon. Okay, so I can give you a explicit example. Very good, very good. Okay, so the first thing actually I want to tell about is how to deal with this gluon coupling, because if you talk about the Qcd axiom, this coupling will always be there, okay? So we need to face that. It's a model independent contribution in this respect. By model independent, I mean that if you want to solve the strong CP problem, you have this coupling here. And if this, I mean, let me first discuss two extreme cases, okay? Above the QCD phase transition, this coupling mediates axion production through gluon scatterings and quark scattering, and these quark and gluon scatterings, okay? And the evaluation of this effect is not so easy because there is some unpleasant infrared behavior, okay? This is due to the long range of gluon-mediated interactions. It's something that, for example, happens for the gravitino as well, if you also are familiar with the gravitino physics, the production at high temperature. And so you need to do a thermal field theory treatment. And I believe this is the paper Maxime was referring to, this paper from 2013 by Salvio, Strumi, and Xue, that took care properly of this infrared behavior. So this is high temperature. Low temperature, you have pion scattering. You have that this operator induces, you can basically doing just with a simple Carrel-Lagrangian, you can derive this vertex and then you can compute the cross section. And a rather recent result, by recent I mean 1 year ago from this paper by Illusio, Martinelli, and Piazza, they showed that if you consider this pion scattering and you want to make sure that you have perturbative control, what do I mean by perturbative control? That the next to the leading order correction in the Carrel-Lagrange analysis is smaller than the leading order, okay? They found that the temperature has to be below this value. Okay, 62 because they derive the perturbative region as a given fraction between NLO and LO. This is of course conventional, but you have to be in this range. Okay, in particular, you cannot treat kaons with this formalism.
Is there a reason why this is so low?
So I also spoke with the authors, and I'm not aware of a simple reason. But as I will show, actually, for the analysis we will do, this specific value will not matter too much. Okay.
One reason I can guess is that because it's sort of a high dimensional operators that you interact with, that your emission is probably peaking at energies that are quite a bit larger than temperature. Like if you take a solar axion spectrum, its maximum is at 4 keV or something like this, where the temperature is 1 keV, right? So maybe the bulk of emission happens at like 4 times this temperature, and it's probably possible to understand that.
And then 4 times 6 is 2. Okay, then that will make more sense. Okay.
Something, but still, it's still low, right? It's surprising, yes.
Yeah, I was also surprised.
The eta, as we know, right, decay, if you treat it in leading order, predicts the leading order of chiral perturbation theory predicts answer that is wrong by a factor of 3. So you need to take corrections into account to get, for example, eta decay right, just to regular pions.
Okay. Okay. So actually, as I said, I will take this number seriously, but it will not have any huge impact on our findings for the reasons that I'm about to show. So this is a plot taken from the paper by Salvio, Strumi, and Xue from 2013. And as a function of the temperature, there is the axion production rate in some convenient units, say T to the 6th FA squared. And the line I want to focus is the red line, because they did more than the gluon coupling, but here I'm worried about the gluon coupling. And you see that the gluon coupling here is this solid line. The dashed line is some previous result that this paper corrected. So let's focus on the solid line. So what was known before our paper was the result of gluon scattering contribution, but only above 10 to the 4 GeV. You see, this horizontal axis starts at 10 to the 4 GeV. And this is already a limitation because we want to go to lower energy. We want to approach the QCD phase transition. And so that's one problem. Well, I mean, one problem. It's something that we need to extend. Another issue, as Tony mentioned, in the case VZ, you have these chiral quarks, these heavy PQ quarks. And you have the contact dimension 5 operator only after you integrate them out, okay? For the DFS, it's even worse. You have this operator with gluons only below the top quark. I mean, you do not have new fermions that carry colors and PQ charge. These are the standard model quarks. So this plot assumes the existence of this contact interaction with gluons all the way up to 10 to the 12, okay? So these are two things that we improved, okay? The main one is actually to extend this plot to the left, okay? Because we want to consider what happens as we approach the QCD phase transition. So here is a result from our paper. In this case, we show the rate gamma 8 times the decay constant squared, because the rate scales like 1 over FA squared, just by dimensional analysis. So the first thing we did was to extend the paper that I mentioned in the previous slide in this range at lot. You see now the horizontal axis, you see the temperature, 10 to the 2, 10 to the 1. And the challenge here was that you have massive quarks, okay? So you need to decouple the quarks at their mass threshold, and you need, and of course you have a strong coupling constant that runs much faster, okay? So we extended the rate in this region, and we stopped at a couple of GeV, okay? We said we trust QCD perturbation theory up to here. Then here is the other plot for the pion scattering, and this is now stopping at 62 MeV. That's the number we just discussed together, okay? And so there is this gap to fill in between. Filling this gap, of course, it's very challenging because there are many resonances here. So we said, okay, what happens if we did a smooth interpolation between these two opposite regimes where we have perturbative tools to compute the rate? And by the way, we also did the interpolation extending the pion rate to 150 MeV, slightly higher. And the result is basically insensitive to if you stop at 62 or 150. Now, a couple of comments on this interpolation, because I don't want to tell you that we did a calculation of the rate, a proper calculation of the rate in this regime. There are resonance around here, but of course, this resonant behavior will be subject to two effects. First, we need to compute thermal averages. Okay, this rate is the result of a thermal average. So you can have a resonant cross-section, but once you take a thermal average, this will be smoothed out. Okay, that's the first thing, but that's not the most serious one. The other one that made us confident that this is something that we can use to make predictions is that this rate is not the observable. The observable is delta N effective. This rate is a function that we will use to feed the Boltzmann equation. So the real question is, how is delta N effective sensitive to variation of this rate in this intermediate region? And we try to perform different interpolations. We even changed it by a factor of 2, the rate here. And basically our findings are solid, okay, if we consider different interpolation in this intermediate region. I have a backup slide if you're interested later, where I can show you that this is not a main issue, okay? So what we did in this intermediate region was to interpolate the two opposite regimes. This plot shows you the interpolation for the case of the coupling to gluons. Of course, if you consider the DFSZ model, you have coupling to gluons, but you also have coupling to the light quarks. But this procedure can be done identically. The only difference is that the rate here and the rate here will be different, because here you will have contribution from also other standard model particles. And here the coupling to pions will be different, because if you couple to light quarks, the coupling to pions will be different. Okay, so let's now discuss the two most popular UV completion and how delta and effective comes in these cases. Okay, the first one is the KSVZ. So KSVZ, here I have like three as a function of the, so as a function of the energy. Here I have the high energy, here you have the low energy. You have a complex scalar and this psi. The psi, these are the heavy quarks that Tony was mentioning before, and these quarks carry Pechequin charge. Now imagine that the mass of this psi is less than Fa. So you end up in this intermediate region below Fa, where you have these quarks in the spectrum. Okay, this could be 10 to the 5, 10 to the 6 GeV, okay, some intermediate scale. It's a parameter of the model. And only after you integrate them out, you recover this dimension 5 operator between the axion and the gluon. Okay, so that's the KSVZ axion, and this is the rate for the KSVZ axion. So you see that you can also see the effect of this quark psi. That's the question Tony was asking before. So at temperatures below, here we took 10 to the 5 for illustration, okay? Below the mass of psi, you have this t to the 6th for the rate, okay? And this is just something you can guess from dimensional analysis, because it's a dimension 5 operator mediating the production. But here you have t to the 4th, and you have t to the 4th because when the temperature is above the mass of psi, the production is mediated by a normalizable operator. Okay, and so dimensional analysis, even in this case, can predict the right behavior of the power law for this rate. So now we have the rate. I mean, the QCD phase transition, I already told you how we dealt with that, but we have a rate that is valid at any temperature, okay? This detail of the psi, we did that for completeness, but we know that this psi is a fermion that carries color. So if it carries color, it cannot be too light. I mean, it cannot be as light as the weak scale. We should have seen that. So we took 10 to the 5 here for illustration. It could be 10 to the 4. It cannot be here, okay? And we are interested in production of axions here or here. If they are produced here, they give the famous 2.7%, and it's something that's barely within reach.
But can I ask a question here? Because
Sure.
there's a trade-off here, right? Because you're taking a very small Yukawa coupling here for these KSVZ quarks, right?
Yes.
And so that then affects also the production. So you'll have a trade-off if you want to see this effect, right? Is that right?
Well, I mean, if you look at the Lagrangian, yeah, so
it'll be M
the coupling is the mass of psi divided by the VEV. So it's basically the Yukawa. Yes.
Yeah. But you're saying that you can still see this effect even though the Yukawa
No. I say that you, even if this effect is able to thermalize the axions, it will happen at such a large temperatures that the effect on them, delta and effective, is not
exactly. Okay. I see. Yeah. Thanks.
Okay. Thanks. So here are some solutions for the Boltzmann equations. This is the famous plot y versus x. Y is the comoving density, and x is the in this case, I think it's a 1 GeV divided by the temperature, so it's a dimensionless temperature. We picked here 3 different values for the decay constant, and they correspond to a final delta and effective, which is at the bound of the current experiments, and at the edge of the future sensitivities, okay? And that makes sense, of course, because Planck excludes something smaller and the future experiments will exclude larger values of the decay constant. And here is the final plot for the KSVZ. The final plot is delta and effective as a function of the only three parameters of the KSVZ model, which is FA, or if you wish, the axion mass, okay? So FA here, axion mass here, they are the same. Just for clarity, we fix the mass of this fermion to 10 to the 5, but as I just said, it doesn't make any difference. And there are different lines here because they correspond to different temperatures where we begin the Boltzmann evolution, okay? And we set the initial value of the axion density to 0. If we set it to the thermal value, of course, we are along this line here, okay? And if the temperature gets larger than basically the fermion mass, this red line, then you do not have sensitivity anymore on the initial temperature because above the fermion mass, you have a renormalizable coupling, so the production is infrared dominated, okay? Just again by dimensional analysis. If you produce axions with a dimensionless coupling, so it's a renormalizable operator, and so it's infrared dominated. So if you evolve the Boltzmann equation much, much higher, starting from much, much higher than the fermion mass, nothing will change, okay? So this red line is for any initial temperature above this value. Of course, if f gets small enough, all of these lines will converge to a single line. What does it mean? It means that you achieve thermalization. So here is the vertical line, which is the stellar bound we were discussing before. So this is bound coming from supernova, and this is for the KSVZ axion. So you only have the coupling to gluons. Okay. Of course, if you also have coupling to electrons, as it will be the case for the next case I'm about to show, then the bound will be stronger. Okay, that's the DFS axiom. For the KSVZ, you only have coupling to gluons, and that's the bound. Of course, this bound comes with many caveats. Okay, it comes with many caveats because there is a lot of modeling on the supernova. There are several assumptions, and you see that even if you do not consider the supernova bound, then Planck is excluding values of the axion decay constant of a factor of a few times 10 to the 7. Okay, and the future CMB surveys will exclude this region here. Coming back to the first question, one of the first questions that Tony asked me about the warp dark matter bound and the effect of the axion mass, you see that we never reach 1 electron volt. Okay, so we safely neglect basically we take the axion as a massless particle at recombination. There is no effect given by the axion mass. But as I say, this is something we are studying now, and we are collaborating with people from Planck. And of course, our job is to provide them with the rates to predict the abundance correctly. Raymond, you have a question?
Yeah, so
Yeah.
can you think of this Ki as the maximum temperature of the universe? For example, the reheat temperature after inflation?
Exactly. So this could be the reheat temperature, and if it's above this value, then everything will be described by this. So even if you have a reheat temperature of 10 to the 10 GeV, you still have to look at the red line.
Okay. And does the thickness of the lines mean anything?
Good. Sorry, I didn't say that. The thickness of the line is that we use two values for G star, two data set for G star, you know, the number of effective degrees of freedom. And just to see the impact of G star on the prediction. So I can give you details if you want.
Okay.
On G maybe at the end I can tell you what we did. And
okay, thanks.
but the thickness is just due to two different data sets of G star. So we shaded the region in between to give you a feeling of the effect.
Yeah, thank you.
Okay, so I can quickly tell you the DFS Z story. Here you have the 2x doublet. First of all, you do not just have one X doublet, you have 2x doublet. And the combination HU, HD is charged under the Patriarchal symmetry. So basically, below the Patriarchal breaking scale, you have this coupling of the axion with the X doublets. And then once you go to low temperature, you can write down this effective Lagrangian with dimension 5 interaction between the axions and the standard model fields. Here I put all of them. Of course, you have the gluons. The gluons are always there. For the DFSZ case, you also have the electroweak gauge bosons, and you have standard model fermions. I put for completeness also the Higgses, even though these operators are redundant, they can be redefined away. Okay. The message here is that the prediction is a bit more difficult because you couple to all of the standard model particles. And here is the result. There is a free parameter. In this case, we have two free parameters. One is FA as usual, the other one is tan beta. Tan beta is the usual ratio between the values of the X fields. And you see here you have a mass threshold, which is the mass of the heaviest X bosons. So here we work on the decoupling limit for illustration. I mean, now I hope it's clear that I care about axions produced below the weak scale. Okay, so if I put MA here or here, we can do that, but we prefer for illustration to separate this mass scale, the mass of the pseudoscalar in the 2x double model from the electroweak scale. And here you see, as you go across this mass threshold, the rate changes the power law. Here you have a super normalizable coupling, okay, with the X double. You have a dimension 1 coefficient. Then you have the usual dimension 5 operators. Here you need a chirality flip that is provided by electroweak symmetry breaking fermion masses. So you recover T to the 4th. And here, unlike the KSVZ case, you still have a non-vanishing rate because you couple to electrons. So even as you go below the pion threshold, the rate doesn't go to 0. Of course, it's very small. Why? Because it's proportional to the electron mass. Okay, the electron mass is very small compared to the other fermions. So here again, I have a production of the axions in the early universe as a function of the temperature. We fix this value to reach the bound and the projections, and the same plot for delta and effective as a function of FA. I would like to put some emphasis here on this white dwarf exclusion line. As I said, in the DFSZ axion, you also couple to the electrons. So the stellar bounds are because you have this additional constraint. And so you see that for the DFSZ axion, this future CMB experiment can still be sensitive to some region, but of course, it's smaller than before, the allowed region. But let me emphasize once more that these gray bands, they have caveats, okay? So I think it's good to have some complementary probe in this region. And this is the one we suggest with the CMB.
Sorry, let me just come back to the stellar constraints. I mean, there are some stellar constraints which are stronger than the ones you're showing here. Now, there might be some model dependence, but you're working within a model, and so.
So which ones you have the red?
Well, I don't have in top of my head the reference, but usually Raffelt, I don't know, you look at the reviews by Raffelt, whether it's from Red Giants, you know, the numbers that I remember are more between 10 to the 9 and 10 to the 10 is a lower limit.
No, so I remember that so of course we are aware of these other bounds. We found that for these models, the Red Giants bound were more or less around this one. And so that's why we showed only one in the plot. But they fall in this range. They fall in this range here. I don't have the references here with me now, but I can quickly find. Maybe I can find it at the end. I can give you the precise number. Okay.
Okay.
But
But I'm pretty sure there are constraints that are higher. Now, they might not apply to what you're doing. That I don't know. But I think there are you know, even in the reviews, there are limits on the mass, which are stronger. I mean, it's usually the limit on the mass that they're quoted as, but it's the same thing.
yeah. I mean, I'm not aware of bounds in this range from stellar physics for these models, at least. We check the, you know, you look at the PDG review, for example.
Yeah.
The red giants is something we check, that I remember, and it falls here. So we didn't want to put too many lines in this plot. In the paper we wrote, look, there is also red giants bound, is more or less there, so we just show one. Okay, but I mean, maybe at the end we can look at precise numbers. Okay.
Okay. Yeah.
Okay, now in the last 10 minutes, I believe I have 10 minutes, I can tell you something similar but different at the same time. And this is something that I did in this paper here with one of my postdocs, one of the postdocs that was also in the previous collaborations. And it's on flavor violating couplings. Okay, so now I consider coupling to fermions, so derivative axion coupling to a superposition of vector and axial currents of fermions, but this is not diagonal in the flavor. So in particular, I don't want these two fermions to be the same. And you see, this could be up type quarks, down type quarks, could be leptons, charged leptons. For neutrinos, they are suppressed by the mass. Because you can integrate this operator by parts and you recover the fermion masses, okay? But now, since they are flavor of diagonal, even the vector currents are there, because you don't, once you integrate by parts, you don't get the cancellation that you get for flavor conserving couplings. And these are the target of several terrestrial experiments. For example, there are very, I don't know, meson decays, like B meson decay, kaon decays, like rare decays with missing energy in the final states, that from the quark point of view, they can be thought as this quark decaying to this quark and the axion, okay? They're also motivated theoretically. There are models that predict these flavor violating couplings. And so we wonder about their role in the early universe. And there were studies before ours, including by myself, but somehow people only included decays in these studies. So they considered the axion produced from the decay of this quark to this other quark. I'm assuming this is the heavier one, okay, and the axion, but they did not include scatterings in the production rate. And the scatterings are important, especially for quarks. Actually, for leptons, they do not make much of a difference. But scatterings are important because it's proportional, the scattering rate, to the strong clapping constant. Once you attach here a quark and then a gluon, then you have a strong coupling constant that gets large as you go to lower temperature. And this strong coupling constant does not appear in the decay rate, okay? So since the main subject of my talk was about the papers from last summer, I will just give you the final results, okay? For leptonic flavor violation, here I report terrestrial bounds and cosmological bounds. So the orange bands are bounds from experiments on the Earth. There is also a supernova bound in the case of muons. And then the green bands are the bounds from cosmology, current bounds and future bounds. So the faint regions are about the future, and the darker region are the present bounds. So you see that Planck is doing already pretty well, because in some cases better, like here, in some cases slightly worse. And then also in the future, these bounds will be competitive with the one from experiments in the Earth that will search for these rare decays of charged leptons. The case of hadrons, of course, is richer because you have way more options and also more experiments. But the message is pretty much unchanged. You see that these green bands are always as good, in some cases better, in some cases worse, than current experiments. And in the future, they will reach values of this F around 10 to the 9. So this F, I didn't say that, but it's defined as the inverse of the axion decoupling, the axion decay constant divided by these dimensionless coefficients. So we pointed out, without relying upon a specific UV completion, but there are, as I said, these flavor violating couplings are also motivated theoretically within frameworks that connect the flavor structure of the standard model to Pei-Check-Quinn physics. We pointed out that these effects on the CMB is a complementary probe of flavor violation in these Pei-Check-Quinn models, complementary to the experiments on the lab. Okay, so I come to my conclusions. We have one of the most motivated particles for physics beyond the standard model. The axion is motivated by the strong CP problem. It's motivated by the fact that it provides a viable dark matter candidate, and the dark matter is the so-called cold axion population. So what I told you about today is about this hot axion population. This is a complementary tool to probe Pei-Check-Quinn physics and also to probe flavor violation from my more recent papers. You can extend this analysis to UV completions, to other light particles beyond the Qcd axiom. So today I told you just what I did, which is the Qcd axiom in the two simplest UV, well, simplest, yeah, the two most popular UV completion, but of course these are not the only ones, and in principle one can repeat this analysis also for other UV completion of the Pei-Check-Quinn mechanism. And in the end, I believe that the message will be the same. This hot axion population is a complementary probe that you can use to constrain Pei-Check-Quinn physics. So I thank you for your attention, and I will stop here, and I'm happy to take more questions. Thanks.
Thank you. Let's thank the speaker.
Thank you. Thanks, Tony. I see you.
Any questions from the audience?
Just out of curiosity, so this future prospects for stage 4 or whatever it's called, they are planning of seeing this small addition to n effective equals to 3.04, right? I mean, due to the incomplete neutrino decoupling, they should be able to see it, right?
Yeah. So the goal that they quote is let's see. So here, of course, we don't know the precise number. So we use 3% as a benchmark, okay, for the resolution. Now, an axion or a scalar decoupling much above the weak scale is giving a 2.7% contribution. So that's the goal, okay? I think the target is given by this new physics, but of course the neutrino, I mean the standard model correction to the, once you do neutrino decoupling properly, I think it's 4.4%, the last number. So they should be able to see that.
3.04, right? Or not 4%.
3.04. Yeah, it's they argue about the next numbers. 3.04, whether it's 3.044 or 3.045 is what they argue.
Right. No, but it's
Exactly.
not 3%.
What?
Well, it's percent of a neutrino. It's 4% of a neutrino.
Well, not relative to n equals 3, right?
It's not relative to 3.
No, percent, sorry, percent, I mean with respect to 1. Yes, yes.
Yeah,
So
yeah,
maybe I
okay.
should not use the percent. Sorry, it's yeah. It's a 4% of a neutrino, of a single neutrino, yes.
Okay.
It's my unit, sorry. That's what I meant.
So it's borderline, right? So you'd have to like measure this number carefully, right? For in
Yes, of course.
But even if you measure this carefully, it won't tell you it's an axion, right? It could be
No,
sterile, right?
You cannot say
Yeah.
what it is. So this is first of all, if you don't see anything new, this is a way to constrain your theories.
Yeah.
If you see something, then to be sure it's an axion, you need to look for an axion somewhere else, of course.
Yeah. No, but any kind of signal would be great.
Yeah, no, I would be happy. I would be happy.
And then I just to see the lepton flavor violating constraints. Yes. Did you say that the cosmology beats the terrestrial? Oh, only for tau.
Only for the tau. For the muon, no. For the muon,
not for the muon. I see.
Not for the muon.
Uh-huh.
Yeah, sorry. I mean, the stellar bound issue. I'm pretty sure now. I don't have the.
It's actually this is from supernova. The bound that I just looked one up.
Okay.
And it's now where did I do it? The worst bound that they're quoting in this paper is 10 to the 9. And they're quoting it could be even an order of magnitude larger. And now you want to know the reference. It's a paper by Kiel, Janka, and Schramm from 97.
97.
Yeah.
Oh, okay. But I mean, we took the last numbers from the PDG to make this line.
Yeah, but okay.
Yeah, but so. I mean, I think I'm not an expert on this bounds, but I guess they did more refined analysis of the.
Yeah, well, I know that Janka and probably Kiel, I don't know Kiel, but Janka is is a supernova guy, and so.
No, I was just.
But they're putting an order of they claim there's an order of magnitude uncertainty in their bound. So.
Okay.
As far as I remember, the latest papers on this supernova bound is also somewhere between 10 to the 8 and 10 to the 9. So I'm not aware of any claims from the 90s that went beyond 10 to the 9.
Yeah, I mean, of course,
they quote. I mean, just looking at their abstract now, they say that the resulting axion mass limit depends on the precise couplings of the axion and ranges from 0.5 millielectron volts to 6 millielectron volts. So that's a bit stronger.
Yeah. No, I mean, I wasn't aware of this paper from 97. I just look at the latest references, and you don't find just one number, of course.
Yeah.
There are but all the numbers I found were in this range here. But this seems consistent with the error they quote, Keith, right?
Well, no.
Order of magnitude.
I mean, I think the lower bound, I think their weakest limit is 10 to the 9.
Okay.
I mean, it's not critical, but I'm just saying, I think that's why I was a little bit surprised seeing that, the limits as low as this. I'm sure you can find papers where the limit is this low, but I don't know if that means that, I haven't looked at it recent enough to see, are they criticizing the stronger limits and saying the limits really should be weaker, or they're just doing a different analysis and not getting as strong a limit?
They do a different analysis. So what we did in our paper, we reported several references, and in the plot, we showed the PDG number. The number from the latest version of the PDG.
Yeah, I'm not sure, but if it depends which PDG, as far as I remember, it's been a long time since I've worked on that section, but it's usually limits on the couplings themselves, and then
Of
you
course,
have to,
the PDG gives you a bound on the coupling of the axion between the neutron and the proton, a combination with quadratic coefficients. But then for this model, you can translate these couplings as a function of FA, and you get the bound. So we did this exercise. We found the bound as a function of FA.
okay.
So
Well, you might want to take a look at this paper. As I say, it's first author is Keil, Keil from '97. So I don't know. It might be interesting for you.
Thank you. Yes. I will.
The other thing is just sort of, again, it's a pretty minor point, but you know, the BBN limit on N effective is a bit stronger than the current Planck limit. It won't make a difference on your plot, but it would push it down.
No, yeah. So we in our paper we discussed this, and you're right. I should have put the references, because in the paper we discussed this at length, and then we decided, since they are more or less at the same level, we decided just to do a comparison CMB with CMB. Okay.
Right. Yeah.
But we were aware of that. We quoted all the, I mean, including your paper, and I should have said that. I agree.
Yeah, I have a question about your, in the flavor violating case, you said the CMB stage 4 beats the terrestrial experiments. Just want to make sure the context. CMB stage 4 will beat the existing terrestrial experiment. Do we have any predictions for future experiments?
Both. The color code here is that the dark region, I mean the faint region is future terrestrial experiment, and this region with the vivid color are current bound. So you see that the stage 4 will go above this.
Okay, I see.
So you can compare.
Same coding for the lepton case, right? For the lepton case.
Lepton case the same, but as we just discussed, only for the tau, actually they will be, for the mu1 they will not do better.
Okay, thanks. Yeah, just want to clarify.
Okay, yeah.
Any more questions from the audience? All right, if not, then let's thank the speaker again.
Thank you for
It's very
the
interesting.
invitation and for all the questions, and it's been a lot of fun. I hope we can do in person some other time soon.
Yes, that would be ideal. Yes.